So in this lecture we want to continue with 2 degree of freedom systems, and we basically discuss the process to get the natural frequencies and the mode shapes in the previous couple of lectures, and now I sort of want to apply those procedures to a different type of problem, just to show you the versatility in that approach. So we'll be looking at worked example 41 now, where we have a 2 degree of freedom system. Now I'm going to say, well, there's one mass m1 10 kilograms and a second mass which is 1 kilogram, supported on the top here by K1, which is 30 newtons per meter, and K2, which is 5 newtons per meter. So we basically have this system which just uses 2 springs, but because there's this spring in between mass m1 and mass m2, it's a 2 degree of freedom system because x1, the displacement associated with mass 1, has no simple geometric relationship with x2, the mass associated with the displacement associated with m2. So let's attack these first 2 parts of the problem first. Derive the equations of motion from first principles and determine the natural frequencies and normal modes of the vibrating system. And in the last part, I just want to show you the role of the initial conditions in determining the actual response in terms of time. You have to remember that the normal modes of vibration, or the mode shapes, are relative terms and are not the actual vibrations, right? But we use the mode shapes to get the actual vibrations as long as we know what the initial conditions are. So we'll be working through this problem now. So let's start by working them as variables, and then we'll make these necessary substitutions as we go along with the calculation. So the system we have is really the spring, mass, and maybe I don't need to use a different color this time because the masses are different. We have M1, K1, K2, M2. And for us to calculate the natural frequencies and the mode shapes, it means the system is being considered in free vibration. And free vibration might just mean that we either give M1 initial displacement or velocity, or M2 an initial displacement or velocity, or a combination of both. But the system is just oscillating back and forth with no external forces acting on them, right? Like a forced vibration, no forced vibration. So the whole idea is that M1 is moving up and down, M2 is moving up and down, and then I want to take a snapshot in time. I want to say, well, maybe M1, we're going to say that X1 is positive downward, and X2 is positive downward as well. And maybe at this snapshot in time we choose to take, maybe we can say in a completely arbitrary way that maybe M1 went down by some amount, X1, maybe M2, just at that instant in time that you're looking at it, M1 is located at X1, and then it's located at, M2 is located at X2. And again, at this instant in time, it's perfectly okay for us to choose if we want to look at it when X2 is greater than X1, like it's sort of shown here, or X1 is greater than X2, but I'm going to take it a little bit differently from how I took it in the previous problem, just to show you that there's no difference. But here I'm going to say, well, X2 is greater than X1 at the instant I am looking at it. And now what I want to do is I want to develop my free body diagram. From our analysis in a single degree of freedom, we saw that the weight of the mass cancels out with the static deflection, right? So M1G would have cancelled out with a K delta S1, for instance, and so on. And the same thing happens with a 2 degree of freedom system. So what I'm going to do is I'm going to basically say I'm not going to include the weights in the free body diagram, M1G or M2G, but I'm also not going to include the static deflections of the spring K1 or K2. So in that way, the only forces I actually include are going to be the spring forces due to that extension X1. And since it goes down, the spring tries to pull it back up. Let me just use a different color. Spring tries to pull it back up with K1, X1. And across here, since we said X2 was greater than X1, well, you could see it that the spring is going to be in tension. So if the spring is in tension, what happens? The spring is in tension, then basically what it tries to do is that it tries to pull M2 back up and it tries to pull M1 down. That's what happens, right? Since the spring is in tension. So this just basically becomes K X2 minus X1, right? And if it was if you had considered the case where, or you would have probably, if you look at the case where you would have probably said, well, I wanted to consider X1 was greater than X2, that would have been fine as well. It's just that how the spring would have been in compression and these arrows would have changed their direction, right? And this expression would have been K X1 minus X2 instead. So that's where the difference would have been, but you would have ended up with the same answer, right? And you can try it. Now, once we've done our free body diagram, what did we say was the next step? Well, the next step has to be to develop the equations of motion, right? And let's develop the equations of motion. We want to say for M1, the sum of forces is equal to M1 X1 double dots, and you can see, well, M1 X1 double dot is going to be equal to, and we took down as positive, so then this becomes K1 X1 and this becomes negative. So just going to put this in blue. And then we look at the other force and it's acting downward, so it's actually positive. This force was negative, but now this force is going to be positive, so it becomes positive. Becomes positive, K2 X2 minus X1. X2 minus X1. Now for X2, what are we going to have? For X2, we're going to say that we're going to have, well, obviously it's going to be sum of forces M2 X2 double dot. So what I'm going to have is just, and I'll call this equation 1 here, so don't lose track. But we're going to have M2 X2 double dot is equal to, and what are the forces acting on M2? Well, we see that this is a negative force, right? So it's going to be negative K X2 minus X1. Alright, good. And maybe I can call this equation 2. So let's look at equation 1 and equation 2, and I'm just going to put a little line here, but to show you what I want to do is I actually want to rewrite these things a little bit better. I want to say, well, M1 X1 double dot, and I want to bring all the X1 terms across here, so I'm going to get K1 plus K2 across here, so I'm going to get K1 plus K2 X1. And then I'm going to bring the X2 term across here, and I'm going to get minus K2 X2. that is going to be equal to 0. And then I'm going to do the same thing for M2. Well, I should have had x1 double dot, right? Because it's going to be x1 double dot. Then you're going to have M2 x2 double dot plus, well, let's put x1 first. So let's put x1 first. Not put x2 first. Let's put x1 first, just to be consistent with what we have here. And it becomes minus k2 x1 plus k2 x2. That is going to be equal to 0. Next step is going to be to get your matrix, right? And the matrix basically always takes the same form. You're going to have this little matrix that you expect to be a 2 by 2 matrix, and we're going to have x1 double dot, x2 double dot. We're going to have a matrix here. We're going to have x1, x2, 0, 0. And now we want to fill this matrix up. So what I'm telling you is that the first equation goes in this first row here, and the second equation goes in this second row. So the first question you have to ask, what's the coefficient of x1 double dot on the first equation? It's going to be m1. What's the coefficient of x2 double dot in this equation here, this first equation? Well, there is no x2 double dot, so it becomes 0. What's the coefficient of x1 up here? It's going to be k1 plus k2. What's the coefficient of x2? It's going to be minus k2. Yeah? What's the coefficient of what's the coefficient of x1 double dot in the second equation? 0. Coefficient of x2 double dot is m2. m2. What's the coefficient of x1? It's going to be minus k2. And what's the coefficient of x2? It's going to be k2. And this is really your equation in the matrix form. Now, again, the stiffness matrix has to be symmetric. Notice the diagonal terms, k1 plus k2 and k2, they are obviously not equal. The diagonal terms don't need to be equal. But the non-diagonal terms on this 2 by 2 matrix has to be equal, right, for a symmetric matrix. So the stiffness matrix is basically going to be symmetric. Now, we went through in detail before how you determine the natural frequencies, right? And I just want to look at it from a different not a different point of view, but more so a more procedural point of view, where I want to say, well, this matrix here is what I call the mass matrix, capital M, right? That's this here. And then I want to say, well, this matrix here is what I call the stiffness matrix K, right? Stiffness matrix K. And then I want you to recognize that from the previous analysis that we did in the first couple of lectures, we showed that to calculate the natural frequencies, what we needed to determine was the determinant of the K matrix minus the omega squared M matrix. The determinant, that's what these straight lines stand for. It's the determinant of this matrix must be equal to 0, right? So, in other words, you have what K is, you have what M is. So to solve for the natural frequencies, we showed that you needed to let this determinant be equal to 0. Now, that becomes relatively simple, because what you're saying is that you want your, and I'm going to put in the K matrix now, and as you get better at it, you'll be able to do it much faster. But you're going to put in K1 plus K2 minus K2 minus K2 K2. So I'm gonna just quickly scribble these things down. K1 plus K2 minus K2 minus K2 K2 minus omega squared, and you look at it and you sort of remember that it's going to be m1 0 0 m2. But the omega squared term is important, right? And you can go back at the previous lecture and see how we came up with omega squared. But the whole idea is you want this determinant of this expression to be equal to 0. To do that, you basically algebraically sum these two matrices to get K1 plus K2, the determinant is still on the outside here, minus omega squared m1 minus K2 minus 0 by omega squared is going to give you minus K2. And you're going to get minus K2 across here. Then you're going to get K2 minus omega squared m2 across here, which is equal to 0. So you've defined your mass matrix, your stiffness matrix, and then you just need to use this expression to derive the determinant of the matrix you're interested in getting, right? And really, I could actually put the determinant and put this little matrix sign here to show you that this is actually the determinant of a 2 by 2 matrix we're doing. What's the determinant of that matrix? Well, we said it's this term here multiplied by this term. This term minus this term by this term. So you're going to get K2 squared. That is going to be equal to 0. At this point, what we could do is we can substitute in some values. Maybe it'll be a little bit easier for you to see if we do that. So we can look at, let's say, well, we saw K1 was 30 newtons per meter, K2 was 5 newtons per meter, M1 was 10, and M2 was 1. So we can substitute some values here and really have 30 plus 5, which is 35, minus omega squared, and M1 was 1, right? So that doesn't change. M1 was 10, sorry. So maybe we could put that 10 out here. And then we can say, well, K2 was 5, so minus M2 was actually 1, so it just becomes omega squared. And minus K2 squared, which is obviously going to be 25, is equal to 0. And then obviously what we can do is expand this out, and when we do that, what we actually end up with is just 10 omega 4 minus 85 omega squared plus 150 is equal to 0. And of course, this is a quadratic in omega squared. Always remember that. So if it's a quadratic in omega squared, then we can solve for omega squared to get omega 1 squared. So you solve this quadratic, and you're going to get omega 1 squared, omega 1 and omega 2 squared basically being equal to 85 plus or minus the square root of 85 squared minus 4 by 150 divided by 2 by 20. And you work that out, and you're going to assign omega 1 to be the smaller value. So I'm going to put omega 1 squared. It's going to be equal to about 2.5. and it's radians per second all squared, but we'll deal with units after. We get omega 2 squared as being 6. Well, maybe we could put it in now. Squared. And of course, we can go ahead and we can find the natural frequency by just finding the square root of 2.5. So the first natural frequency is the root of 2.5, right? Which is just going to be equal to 1.58. And omega 2 is going to be equal to the root of 6, which is just going to be 2.45. Radians per second. And so we have found the first two natural frequencies. Now we can move on to calculate the mode shapes, right? And remember, the mode shapes just give us an idea of how mass 1 oscillates relative to mass 2 for each frequency, omega 1 and omega 2 separately, right? So there are going to be two mode shapes. Mode shape 1, which corresponds to omega 1, and mode shape 2, which corresponds to omega 2, right? So let's look at that. We can say that how do we determine the mode shape? Well, you need to again remember that to determine the mode shape, the equation we used was really k minus omega squared m x1 x2 is equal to 0, 0. That's the expression that we used. Stiffness minus omega squared m. We found the determinant of this to get the natural frequencies, but then we multiplied it by capital X1, capital X2 to be equal to 0, 0, right? Again, if you want to understand where we got this expression from, go back to the first couple of lectures and you'll see. But what was this matrix k minus omega squared m? Well, we already did it, and it was this expression here, right, in the blue bracket. So it was basically k1 plus, sort of write it back. You could substitute values if you want to. But k1 plus k2 minus omega squared m minus k2 and then you're going to have, well, this should be m1 here, and then you're going to have down on the bottom here k2 minus omega squared m2. So you're going to have m2, and you're going to have x1 x2, and this entire thing is 0, 0. And well, let's just substitute in some values for this matrix, and we'll see, well, since this is really 30 plus 5 minus 10 omega squared, we're going to get, for the first term anyway, we're going to get, write it in yellow, we're going to get minus 10 omega squared. And then minus k2 is just going to be minus 5. We're going to have minus 5 across here. And then we're going to have 5 minus omega squared since m2 is equal to 1. And so we'll have x1, x2 is equal to 0, 0. This is how you find your mode shape. Now, to find the mode shape, what you need to do is you need to take this row and multiply it by this column, right, to get an equation. So in this case, what are we going to get? We're going to get 35 minus 10 omega squared, this term multiplied by x1, we all should know how to multiply matrices, minus 5 x2, and that is going to be equal to 0, right? First term here. You could have gone ahead and you could have used this second equation as well, and I implore you to go ahead, try it. You're going to get the same mode shapes regardless. Now, what are you going to do with this? Well, to get the mode shapes, again, I'm going to remind you that each mode shape corresponds to a natural frequency. So we're going to say, considering omega 1 squared, I'm going to consider the first natural frequency, and omega 1 squared was 2.5. So just considering omega 1 squared, which was 2.5, it follows that 35 minus 10 by 2.5 and 10 minus 2.5 is 25, 35 minus 25 is 10, so you're going to get 10x1 minus 5x2 equal to 0. So then you make x2 the subject of the formula, and you say, well, x2 is going to be equal to 2x1, right? So how do I write that first mode shape? Well, I write that first mode shape by saying that x1, x2, and I'm going to put 1 here for the first mode shape. It's going to be equal to, when x1 is 1, x2 is 2. And that's your first mode shape. We can draw it. We can say, well, on the y-axis it's amplitude, right? And we're going to have the location of M1 here, and we're going to have the location of M2 here, and then we're going to say, well, maybe this is 1 across here, this is 1, and this is 2 across here. So when we plot this, we start from the fixed end, which is the top. Draw a straight line connecting to 1, because M1 has x1, which is 1, and then M2 has x2, which is 2. And this is really the first mode shape, right? There's no fixed end across here, so we're not going to close it, right? We can use the same approach to get the second mode shape, but now we're going to say omega 2 squared, not omega 1 squared, but omega 2 squared. But omega 2 squared was equal to 6. And we're going to use the same expression, right? So the same expression. Let me bring it down. So again, we're going to say, well, omega 2 squared is equal to 6. And then you're going to get, well, 35 minus 60, which is just going to be 25 x1. Yeah, just be clear, so you'll see how I got it, but it's just 10 multiplied by 6 x1 minus 5 x2. Minus 5, well, it's going to be minus 25 because it's 35 minus 60 minus 5 x2. This is going to be equal to 0, this is going to be equal to 0 as well. And then you find x2, you say, well, what would x2 be? x2 would actually be equal to minus 5 x1. So for the second mode shape, you're going to say, well, I have x1, x2. I'm interested in the second mode shape. So this is going to basically be equal to, when x1 is 1, x2 is going to be equal to minus 5. Then we want to go ahead and plot that. We want to say, well, we're going to have amplitude here. And let's extend this a little bit. You're going to have M1 here. And you're going to have M2 here. Then we're going to say, well, let this be 1 here, Then let this be -5 somewhere way down here. So now we start at the fixed end at 0. We go up to 1, and then we need to sort of come down directly here. Try to do that a little bit better. We want to end up at -5 here. So it just becomes that. Yeah. So it should be a straight line between this point and this point, right? What do you think this point is here? This point is a node. You should remember what a node was. You should remember what a node was. You should remember what a node was from the first example. It's a point where it remains at rest at all the time. As the system oscillates side to side, up and down, it remains at rest all the time. So this is basically your second mode shape. We will continue with this example to calculate the actual response due to the initial conditions in the next video, and you'll see how the first and second mode shapes come into play to undertake that calculation.